Hello, everybody. So far we've seen how to integrate several different types of functions, but always the method that we pick is highly dependent on what we're integrating. So we might do integration by parts or trig sub or partial fractions and so on, depending on what the thing we're integrating looks like. But there are several things where there isn't really an easy strategy to write what we're integrating in terms of simpler functions. For instance, if we try to integrate e to the power of x squared, then it wouldn't have a nice integral or antiderivative in terms of anything we're used to. And one possible strategy to fix this problem or to overcome this problem is to write functions as sums of simpler functions and then integrate that instead. So the direction we're heading is we want to understand how to write functions as infinite sums or infinite series of simpler terms. And before we can get to series, which are infinite sums, we need to understand sequences. So let's get started with sequences. For a while, it seems like we're going to forget about differentiating and integrating things, but then we'll come back to that or circle back to that in a little bit of time. Okay, so let's start with 11.1 and 11.2 will be series. So firstly, what is a sequence? A sequence is just a list of numbers in a definite order. So there are a bunch of numbers and they have an order. There is a first term, there is a second term, there is a third term, and so on. So typically we write them as A1, A2, A3, AN. So first term, second term, third term, and depending on the sequence, these will be different numbers. And they could have finitely many terms or infinitely many terms. Just depends on the sequence. It might have 10 terms, might have 15 terms, or it might go on forever. And we are going to be mostly interested in the infinite sequences, so the sequences that go on forever. So there's first term, second term, third term, so on and so on and so on. It just keeps going. And okay, there are different ways to represent sequences. So right now we're thinking of an abstract sequence. So you could write down all the elements. That would be one way to represent a sequence. Or you could write down the nth term called AN. So you would have some formula for AN. And if you want, you could also say what is the starting term and what is the ending term. So here you could say AN starting with n equals 1 or AN starting with n equals 3, and so on. So that's enough abstract stuff. Let's see some sequences. So we can represent sequences in different ways. For instance, here is a sequence 1/2, 2/3, 3/4, and so on. Each time the top is going up by 1 and the bottom is going up by 1, and the bottom starts with a 2. So you can think of this term as the sequence n of this sequence as n over n plus 1. Here the nth term is n over n plus 1. So I could write out the elements of the sequence as we did here, or we could write an is n over n plus 1, just telling you what the nth term is, and then you would get the rest of the terms by plugging in n equals 1, n equals 2, and so on. And you could also say, okay, it's n over n plus 1, and I start with n equals 1. Okay, similarly here, for instance, the square root of n minus 3 is our nth term, but we only start at n equals 3. We could equivalently say an is the square root of n minus 3 for n bigger than 3, or we could list out all the terms, right? If we start with n equals 3, the first term will be the square root of 3 minus 3, which will be 0. Second term will be the square root of 4 minus 3, which will be 1. Then we get square root of 2, square root of 3, and so on. So typically we represent sequences by listing the terms or by writing the nth term. But not every sequence has a simple defining equation, meaning it's not always possible to write a formula for the nth term. For instance, say the sequence Pn, where Pn is the population of the world in year n, starting at whatever year you like. Could be year 0, could be minus 2000 BC, whatever you like. Just Pn is the population of the year starting of the world in year n. All right, it's clearly a sequence, right? If you keep going, it's just a list of numbers and they have an order, so it's a sequence. But I can't tell you what is P2021 or what is P2022 or P2023 or whatever is going forward in the future. It depends. Or another kind of very popular example is the Fibonacci sequence that appears in lots of places. So this is a sequence Fn, which is defined recursively, meaning that we define the next term based on the previous terms by the following formulas. So we start with the first term is 1, and the second term is 1, and then this complicated looking equation just says that the nth term is the sum of the n minus first term and the n minus second term. So to get the next term along, I just add the previous two terms. So it starts with 1 and 1, as we said, then we add those together, we get 2. Then we add the previous two terms, 1 and 2, we get 3. Then we add 2 and 3, we get 5. Then we add 3 and 5, we get 8, and so on. So clearly it's an infinite sequence. We can always generate the next element. But however hard you try, there isn't really a nice formula for the nth term. You just have to keep calculating. Okay, so let's go to the next example. For instance, here is a sequence. Some sequences you can find the nth term if you're not already given the nth term. For instance, here is a sequence 3 over 5 minus 4 over 25, and so on. And if we look at what is happening there, we start with a positive, and then we have a negative, and then we have a positive, then we have a negative. It alternates each time. And it starts with a positive. So if you have an alternating sign, you can always represent it as either minus 1 to the n or minus 1 to the n minus 1. Here in this case, it's going to be -1 to the n minus 1 because we want when n equals 1 that it should be a positive sign. So we're going to choose -1 to the n minus 1. It would be equivalent to have -1 to the n plus 1 here. -1 to the n minus 1 is the same as -1 to the n plus 1. Okay, the top each time, if we forget about the sign, we are going 3, 4, 5, 6, 7, and so on. The top is going up by 1 each time, and it starts at 3. So it's going to be n plus something, and when n equals 1, we want it to be equal to 3. So we have to have n plus 2. And the bottom is multiplied by 5 each time, and it starts with 5. So it's going to be 5 to the n. So if we put all that together, the nth term is -1 to the n minus 1, the minus capturing the sign, n plus 2 capturing the change on the top, and 5 to the n capturing the change in the point. So here is the nth term of our sequence. Okay, how can we represent sequences? So like with functions, we have a way of representing them visually. We do the same thing with sequences. So we can either just plot all the points on a number line, or we can plot a graph of n against an. So for instance, here's the sequence n over n plus 1. It has terms 1 over 2, 2 over 3, 3 over 4, 4 over 5, and so on. The 99th term would be 99 over 100. And here it is represented in 2 different ways. So the first way, we just plotted all the points, or I plotted as many of them as I could squeeze in. Right, we started with a half, then we have 2/3, then we have 3/4. We just plotted them on a number line, and clearly they are spiraling in and getting closer and closer to 1. And then in the second possibility, I plotted n against an. So when n equals 1, we have a half. When n equals 2, we have 2/3. When n equals 3, we have 3/4, and so on, listing all the terms. So it just depends on the situation which way you want to graph them. Usually I will use the second way, which is to graph n against an, because then you can clearly see what is the first term, what is the second term, what is the third term, and so on. And in the number line picture, you can kind of see that, but if the sequence alternates or goes back on itself or does something weird, if it's not just always going up, then it's going to be hard to figure out what is the first term, what is the second term, and so on. So I tend to use the second way a little bit more. Okay, and as you can see, by the way, from these pictures, clearly something is happening. As n gets larger, the sequence is spiraling towards 1 on either picture, right? You can see it here, the 1, or on the graph, you can see it's clearly approaching the value 1. So if only there was some way to capture this, surprise, surprise, there is, and it's called a limit. So this sequence would have limit 1, for instance. So what do we mean by limit of a sequence? And the definition is going to be very similar to a limit of a function. So let's suppose we have a sequence, and L is a finite number, and we want to define what it means for an to tend to L. Okay, and the thing we ask is that the values of our sequence can be made as close as we like to L by making n sufficiently big. So if I want the values to be within 0.1 of L, I can guarantee that provided n is large enough. Or if I want to be within 0.0001 of L, I can do that provided I take n sufficiently large. And what do we mean by made as close as we like here? So they should get close and they should stay close. So I should be able to look far enough along, and then they will always be close and they will always stay close. So they're never going to kind of zoom away at some point. They should get close and stay close. Okay, so this is what we mean by an tending to L, or an having limit L. And we write the limit as n tends to infinity of an equals L, or an tends to L as n tends to infinity. So it's very much like functions, except rather than a function f of x, we have a sequence an. And n is getting large rather than x is getting large. But n can only be whole numbers, so it's not exactly the same thing. Okay, so if the limit exists as a finite number, we say the sequence converges, otherwise we say that it diverges. So for instance, here is the idea in a picture. We have a sequence, here are the points, okay, they're going up and down, whatever. We have L that I claim the sequence is approaching. And what is this horizontal strip that I draw? So remember we're saying that the values of the sequence, the values of an, should be made as close as we like to L. So how do we represent that on a picture? If we're getting close to L, that means we can choose a narrow band around y equals L. So however narrow a band I made around L, so in this case I did these dotted lines, I can guarantee eventually the sequence is going to stay inside that and not go outside, provided I look far enough along. So if I look at the start of the sequence here, it's just a crude picture. I didn't draw that many terms. If you look at the start of the sequence, the first, say, 4 terms, they're outside the band, but that's not a problem because if we look far enough along, then eventually I'm inside the band and I stay inside the band. But this should be true however close I want to be to L. So however thin and narrow band I draw around L, eventually the sequence should stay inside there. So if you imagine, some tiny, tiny band around L that you can't even see, it would be so small. Eventually, for the limit to be L, the sequence should get inside there and stay inside there. So that's the definition of the limit. So as I pretty much said, for any band around L, the sequence eventually is going to stay inside. If I take thinner bands, I can take it as thin as I like, but then I have to look further along in the sequence for the sequence to be inside. And the sequence can cross y equals L, like here, sometimes it's above L, sometimes it's below L, but it should be getting close and stay close. It doesn't matter whether it's getting close from above or getting close from below, or it's alternating between the two. Okay, one thing that as a pure mathematician, I have to mention, but is not on the exam. So here is my disclaimer, it's not on the exam, I just want to mention it, is here we have everything in terms of words, and it seems a little bit wishy-washy. What does it mean that the values of the sequence get as close as I like? And things written in terms of words tend to be vague and easily confused. So there is a way to make everything precise. So we say the limit of an is equal to L. If, remember, we said however close we want to be to L, okay, there is some way to quantify that. For any epsilon bigger than 0, this is going to measure how close I want to be. So for any epsilon bigger than 0, however close I want to be, there is a whole number n, so that if I look at all the terms after n, so if I look later, far enough along in the sequence, I look all the terms bigger than n, then I can say that the absolute value of an minus L is less than epsilon. So what does this mean? This absolute value just measures the distance between an and L. So we're saying the distance between an and L is less than epsilon. So just to say one more time, and then I'll never repeat this again. However close we want to be to L, whatever epsilon we pick, we can always find a whole number n, so that if we look after the nth term, then our sequence is always going to be a distance, it is going to be close to L. It's going to be a distance less than epsilon. So there is a way to make all this precise, and pretty much all the results we talk about in Calculus 1 and Calculus 2, they have these rigorous definitions in terms of symbols, in terms of things we can actually calculate and do things precisely with, even though we kind of skate over some of the details in calculus. But hopefully I can give you a flavor of why things are true for calculus. Okay, so back to things that are on the exam, and we should understand, is we said that the limit of a sequence and the limit of a function look kind of similar, right? Oh, there is the same kind of language, or if you phrase it in terms of formulas, the same formulas. However close we want to be to L, we can guarantee that provided n is sufficiently large or x is sufficiently large. Okay, so we can recycle a lot of the limits we have for functions. So if if our sequence comes from a function, if instead of f of x, it just looks like f of n, say I start with the function 1 over x squared, I can get a sequence from that just by replacing x by n. From 1 over x squared, I would get the sequence 1 over n squared, just replacing x by n. So if my sequence comes from a function, and I know the limit of the function as x goes to infinity, then the limit of the sequence will be the same thing. So using this, we can recycle a lot of the results we have for limits of functions to give us limits for sequences. But of course, not every sequence comes from a function, as we'll see later. So here's an application. The limit of 1 over n to any positive power is equal to 0. Because the same thing is true for functions, and we've already seen that before in Calculus 1. For instance, 1 over x goes to 0 as x goes to infinity, so 1 over n goes to 0 as n goes to infinity. Or 1 over x squared goes to 0 as x goes to infinity, so 1 over n squared goes to 0 as n goes to infinity. Okay, or we can even recycle other limits. So for instance, we know that ln x divided by x goes to 0 as x goes to infinity by L'Hopital's rule. So we can recycle that for sequences, right? Ln n divided by n goes to 0 as n goes to infinity. Just because we can get the sequence ln n over n by using the function ln x over x and replacing x by n. But here we are not using L'Hopital's rule for sequences, that there is no such thing, right? A sequence, we are only allowed to plug in whole number n. So when there's no L'Hopital's rule for sequences, we're just using a result for functions and then passing it over. Okay, so here is the example we talked about. We said 1 over n squared, for instance, goes to 0. 1 over n to any positive power goes to 0. Here it is on a graph. N equals 1, we have 1, then we have a quarter, then we have 1 over 3 squared is 1 over 9, and so on and so on. It gets closer and closer to 0. However close I want to make it to 0, eventually it will be close enough, provided I look far enough along. Okay, then next up we have infinite limits. So it's again very much like for functions. The limit as n goes to infinity of an equals infinity means that we can make an as large as we like by making n sufficiently large, similar to for functions. The limit being minus infinity means we can make the values of an as large negative as we like by making n sufficiently large. So large negative meaning, it's going to look like minus 100, minus 1,000, minus 10,000, whatever. It's going to be large, but the sign is going to be negative. Okay, so here, for example, there's a picture of a sequence which is hopefully tending to infinity. Right, it's going up, it's getting larger and larger and larger. It doesn't have to be increasing. It doesn't have to always be going up. Like here is the first term, the second, the third term, the fourth term, the fifth term, and so on. It's okay if it goes down slightly here and there, but this can still satisfy the definition of tending to infinity. For instance, here, what are we saying in the definition? We're saying we can make the values of the sequence as large as we like. So a way of thinking about that on the picture is to say whatever number I pick, whatever, say, capital N I pick, if I look far enough along, eventually the sequence is going to stay above that line. So whatever horizontal line I pick, eventually the sequence will stay above. So here I drew this line, eventually it stays above. I could draw any line. I could draw a line above your monitor, and eventually the sequence would be coming out of that, or would be above that. Okay, and again, since some sequences come from functions, if we have a limit of a function being infinity, then also the limit of the sequence will be infinity. Okay, and for instance, the limit of n to the r is 0, the limit of n to the r is infinity if r is positive. For instance, just because the same thing works for functions. For instance, the limit of x as x goes to infinity would be infinity. The limit of x squared as x goes to infinity would be infinity. Okay, so the limit of n squared is also infinity as n goes to infinity. Okay, but we said, I kept saying that not every sequence comes from a function, but I never give any evidence of that. So here is a function, a sequence that does not come from a function. So it's n factorial. So for any positive integer n factorial is the product of the first n whole numbers. So 1 times 2, I don't remember why I read it backwards here. 1 times 2 times 3, and so on until we get to n. So for instance, 1 factorial would be the product of the first one whole number, it would be 1. 2 factorial with the product of the first two whole numbers, it would be 2. 2 times 1 is 2. 3 factorial, 1 times 2 times 3 is 6. 4 factorial, 1 times 2 times 3 times 4 will be 24. And so on and so on. You just multiply the first n whole numbers together. And what does that mean for 0? It doesn't really make sense to multiply the first 0 whole numbers together. Doesn't have any sense. So we just have to pick a value for that we like. So separately, we define the 0 factorial to be 1. And this definition, 0 factorial equal 1, is completely separate to the product of the first whole number, the first n whole numbers. It's just a convention, a choice we make for 0 factorial. But there is a good reason for it, that in a lot of places there are going to be, there are going to be formulas involving factorials, and everything is much nicer and the formulas look much more beautiful, which is very important if you choose 0 factorial to be 1. So that's pretty much followed pretty much everywhere. Okay, so this is a sequence. It doesn't come from a function. There is no x factorial. X factorial doesn't make any sense. So it's a sequence. It doesn't come from a function. Okay, but clearly this sequence goes to infinity as n goes to infinity. It gets larger and larger, and it stays large. Okay, so that's everything for this video. So we talked about the definition of a sequence. A sequence is just an ordered list of numbers. We looked at the definition of what it means for a sequence to tend to a finite number L, or to tend to infinity, or to tend to minus infinity. And then we said the definition looks kind of similar to the definition for functions. So if we have a sequence that comes from a function, but that's not every sequence, not every sequence comes from a function. But if our sequence does come from a function, then we can recycle the results we had for functions. Okay, thanks everyone. See you next time.